Okay, so today we are going to discuss a new topic, equilibrium of a rigid body, and being more precise, mechanical equilibrium. So, what do we mean by mechanical equilibrium of a rigid body or an extended body, which is also a rigid body? So, mechanical equilibrium means there is no acceleration, I mean linear acceleration or angular acceleration as well. So, if in a rigid body there is no linear acceleration as well as no angular acceleration, then we can say this rigid body is at equilibrium. And now this means there is no change in linear momentum. So if I'm writing linear momentum, this should be constant as well as there should be constant angular momentum. And these two things will happen when the net force on the body is zero as well as the net torque on the body is zero. And here, if we are talking about net force or net torque, we are talking about external because we have already discussed one thing that internal on a system of particles, internal torque or internal force, these things are not going to make any change in their momentum. Okay, so we are specifically talking about external forces or external torques. Now, there is one thing. If we are choosing a random point to be reference or origin, this force is not going to change. So this is independent of our choice of origin or reference point. But this thing we have to check actually because we have studied this thing already that torque is something R cross F. Then there is position vector involved, and if we are shifting origin, this position vector will also change, and this change will give us a changing torque. Now, is it valid for each and every cases? Because initially we were talking about moment of force. There we have chosen one particle. Let's say we have started with a single particle, and then we said that okay, this is something particle at point P, and it is yes, and a force of F is acting on this particle, and then position vector for this particle is R. Then we can say, okay, torque about this origin will be R cross F. So if we are changing this origin, this R will also change, and consequently this torque will also change. So is it the same case if we are choosing rigid body instead of a single particle? So we are going to check that thing later. Now, a little bit later. Now, these two equations are vector equations. So we can resolve them into their components, and we are talking about Cartesian system. So we can resolve this thing also. And what will we get? We will get that force I x, which is x component of the force, net force actually means this Fi is denoting the total force. Means if there are n number of forces acting on the body or the rigid body, so this I starts from 1 to n, and similarly we can say if there are n number of torques, we can say this I starts from 1 to n. So this is x component of all the forces, and then this is y component, and these all things should be separately 0 in case of mechanical equilibrium. And why I am saying that this all three should be separately 0 as well as in this case x component, y component, and z component all should be 0 to get a complete mechanical equilibrium. And why I am saying that these all should be independently zero? Because these all components are along independent axis. So this is along x-axis, this is along y-axis, and this is along z-axis. And these three axes are independent to each other. Okay. Now what will happen if the net force is not zero, but net torque is zero? So in case net force is not zero, if there is force acting on a system, but there is no net torque, then in that case, there will be rotational equilibrium only. And we can say we are talking about now partial equilibrium. Okay, so rotational equilibrium will be when this net torque is zero. Okay, I can write here zero vector, null vector actually. And what about translational equilibrium? Okay, in the same way, translational equilibrium is when net force is zero on the system or on the rigid body here. Okay, now I'm taking two different situations where you can visualize these two things. Let's say we have here two forces acting equal and opposite forces. Let's say one force is here acting F, or let's say this is minus F, and this direction we are taking positive. So let's say here positive F. So if I'm asking what is the total force on this extended body, you can easily say that in this direction F and in this direction also F, I'm indicating this force with negative sign to say that it is just opposite to this one. So the net force is zero in this case. And what about these two forces are acting along the same direction, and these two forces are equal in magnitude, and now they are acting in the same direction. So there is a complete rotational equilibrium here. Although this body will start accelerating this direction, there will be acceleration here in this direction. There will be change in momentum along this direction, but there is no net torque acting on this body, so there won't be any change in its angular momentum, or there won't be angular acceleration in this. Means angular acceleration will be zero. And what about this case? So equal and opposite forces are going to give us net acceleration zero, and then change in momentum, linear momentum is zero. But now there will be turning effect, and that turning effect will be changing